Okay, this is going to be a video about a compact hydroelectric power plant control system. So this is going to be a presentation. So we have a hydroelectric power plant, a small one. It's intended for small plants. So first, if you look at the system structure, so a small power plant consists of a prime mover, a turbine, a generator, a breaker, maybe a transformer, and a grid. And this system has to be controlled. So normally, a conventional plant is using, let's say, a lot of devices to do this. They have speed controllers, Woodward speed controller, might not be used in power plants. Prime mover turbine, we have a generator, which is controlled by a voltage controller, control the voltage through excitation. And we have a safety system for the prime mover to protect the turbine. We have a generator breaker with transformers and measurements, and then we have a synchronizer, and then we have a breaker protection device too. And these, they interact. For instance, if you have a de-excitation on the generator or something, you should stop the turbine, things like that. And here is to offload when you want to open the circuit breaker, you have to reduce the voltage, and so on. And then you have a control system coordinating all these and interfacing the external world too. With all this, and the idea here is to replace some of these units, or most of these units, by software units in a controller. The protection, the speed controller, the synchronizer, and the safety system can be inserted into a unit as software unit, into a control system as a software unit. And then you have a compact system. We have the power plant. Here we would have the excitation control, and maybe an emergency shutdown system. Here's the compact control system with local operation and then remote operation using OPC. We have this IEC protocol. We have it. We should probably opt for a better protocol like OPC. Show both of those. And also to test the plant, it would be nice to have an emulator of some sort, which could be constructed using frequency converters, motors, permanent magnet generators, and then breaker and measurement transformers here to do synchronization and so on the breaker. It would be nice to have one like that, and it would look like something like that. We have a model that is controlled by a PLC. Here show a schematic PLC with operation. Could use, for instance, web-based operation. And then it is the control system here, over here. And then, as an example, we would use inputs to this would emulate turbine and so on, and power and so on, and do the control. And inside the compact control system, we have control of the nozzles, turbine, auxiliary control, can be hydraulic pumps or whatever, net analyzing. We have a breaker controller, we have a generator protection controller, and so on. And then we have a sequencer to start this in a sequence, run up to idle, do synchronization, close the breaker, and so on. And here too is local operation, could be use Node-RED flows, for instance, and then use a web browser for operation. And this should be or could be an IPC, and here's from Beckhoff, because they have components that are fast enough to do this. Okay. And then we could look at if we don't have a physical system, we have an emulated system, and we could emulate this power plant inside the same IPC or controller, or even on a standard laptop or something that performs the control itself. And then again, Node-RED floats here. It's indicated you could use Raspberry Pi for operation to host these, and so on. A little on software details for the system. Here is a library, and this is in TwinCat, and it would also then, of course, could execute on any Codesys-based system. And here is some a library with breaker protection, circuit breaker control, miscellaneous, power frequency control, phase analysis, raise lower control, synchronization check, and synchronization check enable, net analyzer for 3 phases or 6 phases, the network side, the grid side, and the generator side, and then we have a single phase. And we have nozzle control, a sequencer, set point district, set point priority interface, how you do this. So it's a typical library for modular libraries you can build control. And here are instances of these classes of function blocks, or some of them. So they are kind of, there's quite a bit on it. And these are according to an IEC norm when it comes to the, or roughly when it comes to the input-output naming convention. And also with this, there's a library with this standard IEC, the library components, let's say, with an MA monitor analog, which is a standardized functionality for with alarm limits and so on. And there's a library that you can use here for auxiliary control. Okay, and here is some, and there's also a lot of components in this library. With the for control, we have PID controllers, algorithm and neural net, state space controllers, matrix. There's quite a bit of matrix math used there, a signal process, and primarily low pass filters, which do, because those are most frequently needed. But we have some band pass and band stop filter and stuff also in the library. Okay, and then there is emulation software, hasn't been shown here, but here is an emulation for a single turbine with 6 nozzles. Yeah, it's emulated down here, but these are just building blocks, so Lego blocks that you can build any emulation here in the same IPC as you have your control. And then there's a little tool to do the test on this emulated plant. Here is operation and control. It's built in Node-RED. It's okay. Node-RED. Here's OPC UA communication. Node-RED has an OPC UA client, so it's possible to communicate with the system. And we use, of course, OPC UA because then third-party applications could get hold of information from the system on a standardized way. The IEC, the 61850 norm, well, it is a norm. Who wants to use it? Okay, so you could use any standard browser to do this control. Here's just an overview of the main. Here's an active power. So you go a little, but you can set the active power here, and is the actual value. And of course, the active power for this plant could also be set from a remote system. And we have an event system. That's a nice thing because in OPC UA, the timestamp when propagates. So here's an event system, and here's an exception system, alarms for this. And then you can clear the events. So okay, this is to just show you. This can also be operated on a tablet or mobile phone or whatever. Okay, so here are some events, with events that in the system. And here is the power system, the main power system with the sequence control and current and voltage and so on. And here is some, we can look at that a little later because that's expanded. Not the synchronization. Here's the differential voltage dual synchronization. Here's the correlation between the voltages, grid voltage and the generator voltage when the breaker was closed, which means that they are pretty synchronous on the closure. And then we have turbine control on the nozzles, where you can have priority on the nozzles. You can change the priority, and you can have automatic rotation if you want to kind of jog your nozzles automatically. We set up now is that one they peak out one and nozzle 1 and 1, 2, 3, 1 and 4 peak out, 2 and 5 peak out, and then it's 3 and 6 take the rest load. But here nozzle 6 is in manual operation, which means and it has been switched off or closed, so you can only operate on 4 nozzles. Yes. And here's also set point distribution. Now it's automatic from the pneumatic. You do it manually, and there's a vibration that you can have to avoid the nozzles from freezing. And here's the set priority. And here's just an example: auxiliary system, hydraulic tank, and oil pressure. You could have a hydraulic pumps. Here's where you would use the IEC components to do this control. And here is here's the pump and pump coordinator. Here we have 2 hydraulic pump and a pump coordinator, so we have a duty standby system. So if one pump fails, the other one starts. And if you have low pressure, of course you can run both pumps in parallel. Okay, so here is a little on the measurements, that is, and the pumps they are on the right hand side. And now it is for this is from a physical model, but it's the synchronization. And here is a plot of synchronization, and the synchronization is performed right here. And here you can see the curves, and here the breaker is closed, and this is just an expanded, and this is a true-false log. Here is this force, and here is and there is a delay in the breaker. This emulated the approach to the delay in the breaker, and it's been closed here actually. And of course then the voltages, they are equal, except then for noise, measurement noise, and so on. Yeah, and out of this you can do some articles and write on findings. And what has been done here is a paper with throttling OPC UA communication traffic from the server side. The server side decides when to transmit information, not the client side. So here the communication control is by the server side, and it is on OPC UA, which has been used here exclusively in this system. Via OPC UA, well, it's a modern secure protocol with which is also moving into time-sensitive information flow, which is not needed here because the time-sensitive processing is within the IPC system. Okay, so this was a quick introduction or to a system which is readily programmed, can be used, has been tested on a physical model, and also on an emulated power plant to let's say debug it. And out of this, there's a library with let's say small hydro control components, and there's a standard library according to an IEC norm, and there's a lot of support functions can be used. And it's based on TwinCAT system and some special components, fast and measuring components, the extremely fast processing components in TwinCAT or from Beckhoff to implement this control.